Hi everyone, I hope you're all doing well. Today we're going to continue our discussion on chapter 18. So previously we talked a lot about entropy, and we are going to continue our discussion on entropy. All right, so this time we're going to think about entropy in terms of heat transfer. Specifically between our system and its surroundings. So remember that spontaneity refers to an increase in entropy of the universe. So delta S of the universe is greater than 0. And that has to do with the second law of thermodynamics. However, there are several spontaneous processes in which entropy appears to decrease, not increase. So last time we did talk about several examples where entropy does increase for a system. So for instance, if we go from a solid to a liquid to a gas, entropy is continuously increasing because the particles can move around more. As particles move around more, we have more possible arrangements for those particles. Okay, but what about water freezing? Water freezing is totally spontaneous. We see it all the time, especially if temperatures are below 0 degrees Celsius. Now, the entropy of water during freezing decreases, right? But again, it's a spontaneous process. So let's kind of write out an equation here. We've got water as a liquid, and it is becoming a solid. So that is spontaneous, but delta S for the system is less than 0. So entropy is decreasing because particles are becoming more rigid, so they can't really move around anymore. Okay, so then why is this a spontaneous process? Remember, according to the second law of thermodynamics, the entropy of the universe has to increase. So even if our system's entropy is decreasing, maybe the entropy of the surroundings is increasing, and it's increasing enough that the overall entropy of the universe is increasing. So in our previous example, the entropy of the water decreases as it freezes, but the entropy of the surroundings must somehow increase so that delta S of the universe is greater than 0. All right, so let's see how that could be true. So here's a little diagram. We have entropy, or increasing entropy, on the y-axis. And then we have the change in entropy of the universe, the change in entropy of the system, and the change in entropy of the surroundings. So when the entropy change in a system is unfavorable or negative, just like our freezing example, the entropy change in the surroundings must be favorable and large. So let's see, entropy change in the surroundings must be favorable and large. And that will allow the overall change in the universe to be positive. So for instance, let's just assign some numbers here. So let's say the entropy of the system, we can see it's negative. So let's say that's negative 40 joules per Kelvin. And then we can see that the change in entropy of the surroundings is positive. Now, this must also be larger in magnitude than delta S of the system. So let's say it's 41 joules per Kelvin, and it's positive. So now when we add everything together, so we've got delta S of the system, negative 40, plus delta S of the surroundings, positive 41. That gives us an overall plus 1 joules per Kelvin for the entropy of the universe. So it is possible to have a system where entropy is decreasing, and yet it's still spontaneous. And again, those are arbitrary numbers I used. Those aren't the actual values. All right, so when we're freezing ice, remember that heat has to be removed from the system in order for it to freeze. So the freezing of ice is actually exothermic, which means heat is released again to the surroundings. So the release of heat energy by the system disperses that energy into the surroundings. And this will increase the entropy of the surroundings. So if we have a beaker of water and it's cooling, then it's going to give off heat to the surroundings until it freezes. So let's say we've got some ice in here now. All right, so delta S of the system again is decreasing because the particles become more rigid. So there's less disorder. But then the surroundings, the surroundings are gaining heat. So the particles in the air, for instance, become more energetic. So they're going to have more possible arrangements, which, going back to our classical definition of entropy, W is the number of arrangements that are possible for a particular thing that we're considering. And in this instance, we're considering the air that's surrounding this beaker. So it's becoming more disordered because we're adding more energy to it. So delta S of the surroundings is greater than 0, and the overall delta S of the universe will also be greater than 0. So the second law of thermodynamics still holds true. All right, so just a quick review here. When a system process is exothermic, remember it adds heat to the surroundings, and that will increase the entropy of the surroundings. When a system process is endothermic, remember it takes heat from the surroundings, so it absorbs heat. And that's going to decrease the entropy of the surroundings. Now, the amount the entropy of the surroundings changes depends on its original temperature. So let's say we're cooling down water and turning it into ice. And let's say the surrounding temperature is above 0 degrees Celsius. So let's say it's 10 degrees Celsius. If we add heat to those surroundings, the temperature change won't really be that significant, right? But if the air surrounding the beaker of water is really cold, so let's say negative 10 degrees Celsius, then any heat added to the surroundings will be quite significant. All right, so let's look at those same charts again, but this time we're going to compare a situation where the surrounding air is low in temperature, and then a situation where the surrounding air is high in temperature. So remember, we're thinking about freezing water. So let's say we're in the process of freezing it, so there's some ice cubes in there, and we're dispersing heat into the surroundings. All right, so if the surroundings have a low temperature, then any heat added to the surroundings will have quite an effect. Whereas, okay, instead of 10 degrees Celsius, let's say the air around the beaker is 80 degrees Fahrenheit, or maybe like 30 degrees Celsius. Then any heat added to the surroundings won't have that much of an effect, right? Because the air is already hot. So with our low temperature, let's just put in there the negative 10 degrees Celsius we talked about earlier. Or we could even do Fahrenheit for that. That's fine. Okay, so if we add heat to a low temperature situation, we have a huge effect on the surroundings. So we can see that the magnitude for the entropy of the surroundings is quite large for the low temperature situation, but then the high temperature situation, the change in entropy of the surroundings is much smaller. So on the left-hand side, the delta S of the surroundings is still greater in magnitude, so we'll just write plus 41 there, than the entropy of the system. But in the right-hand situation where we have a high temperature, let's say the surroundings and the change in entropy is only 20 joules per Kelvin. So we can see on the left-hand side, again, we'll have a positive change in entropy for the universe, but on the right-hand side, we have a negative value. So we'll see a decrease in the overall change in entropy of the universe. So that tells us that water freezes spontaneously at lower temperatures, and it does not freeze at higher temperatures. That's a non-spontaneous process. And that's actually why we need freezers, right, in our homes, because to make ice, we can't really make ice in warm temperatures. We have to cool the water down, and we have to provide energy in order to do that. So we would need a freezer, which needs a lot of electricity, in order to make that process happen. Okay, so anyway, this is all very conceptual, but this is all going to lead to a discussion on free energy later on. All right, so again, just a summary. There is greater impact on entropy when heat is added to surroundings that are at lower temperatures rather than higher temperatures. So again, there's a greater impact on entropy when heat is added to surroundings that are at lower temperature. So again, water freezes spontaneously below 0 degrees Celsius because the heat released on freezing increases the entropy of the surroundings enough to make delta S positive. So if we have anything, if we have a temperature above 0 degrees Celsius, the increase in entropy of the surroundings will be insufficient to make delta S positive. Okay. All right, so now how do we quantify this idea? How do we actually calculate delta S for the surroundings? So remember last time we said that delta S of the system is equal to Q for a reversible process, or the heat involved, divided by temperature. So we could even say that it's delta H of the system over temperature, or the change in enthalpy of the system. So the entropy change in the surroundings is going to be proportional to the amount of heat gained or lost by the system. So the heat of the surroundings, Q, is equal but opposite to the heat of the system. So anything the system loses, the surroundings gain, and anything the surroundings lose, the system gains. So there'll be, so Q surroundings will equal negative Q of the system. Or another way to think of it is delta H of the surroundings will equal negative delta H of the system. Okay. Now, the entropy change in the surroundings is also inversely proportional to its temperature, similar to our change in entropy for the system. So at constant pressure and temperature, the overall relationship is as follows. So delta S of the surroundings will equal negative delta H of the system over temperature. All right, so now we have a way to calculate the change in entropy of the surroundings. So let's do an example problem where we use that equation. So here we're going to consider the combustion of propane gas. So C3H8 is propane, and it reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. And then the change in enthalpy of the reaction is negative 2044 kilojoules. So A, calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. Okay. Oh, let me make sure I'm on the right slide. Yeah. All right, so let's calculate that entropy change in the surroundings. And we said that that is equal to negative delta H of the system over temperature. All right, so delta H of the system, or of the reaction, is negative 2044 kilojoules. So we'll plug that in. But there's already a negative sign there, so we're going to include both of those, which will make this an overall positive change in entropy, right? And then in the denominator, we want our temperature units to be in Kelvin. So we're going to add 273 to the temperature. So that means we have positive 2044 kilojoules. Those negatives will cancel. And then we have 298 Kelvin in the denominator. Okay. So 2044 divided by 298. That should give us a value of 6.86 kilojoules per Kelvin. Okay, now typically entropy is expressed in joules per Kelvin. So remember there are 1,000 joules for every kilojoule. So this would equal 6.86 times 10 to the third joules per Kelvin. So we're just multiplying by 1,000 there. All right, now B, determine the sign of the entropy change for the system. Okay, so for this, we're going to need to consider whether this process is becoming more ordered or more disordered. Now, everything is in its gaseous state, so we can't really consider the entropy of the state there. However, we can count the number of moles on each side of the arrow. So on the left-hand side, how many moles of reactants do we have? Okay, so we have 6 moles of reactants. And then how many moles of product do we have? So we have 7, because 3 plus 4, right? All right, so if we're going from less moles to more moles, are we becoming less ordered or more disordered? Or sorry, less ordered or less disordered? I guess I said the same thing there, didn't I? So we're becoming more disordered, right? So that means that entropy is increasing. So it's greater than 0. Now, looking at A, we said that delta S of the surroundings was positive. So that means that delta S of the surroundings is also increasing. So entropy is increasing. So we'll write delta S of the surroundings is greater than 0. And then for part B, I'm just going to add a little system there for delta S, because in part C, we want to determine the sign of the entropy change for the universe. Okay, so remember delta S of the universe is equal to delta S of the surroundings plus delta S of the system. Now we said that both the change in entropy of the surroundings and the system are positive. So that must mean the change in entropy of the universe is also positive, which is what we want, right? So is the reaction spontaneous? Yes. Remember, if delta S is greater than 0, then we have a spontaneous process. Great. Okay. Oh, and there's a second slide that I didn't need. So last time we worked on an example problem from your textbook where we kind of stepped through different example reactions and figured out if entropy was increasing or decreasing. So worksheet problem 3 goes through the same process. You have to determine how many moles of reactants you have, how many moles of products you have, and then determine if there's more disorder or less disorder for that system. So I'll let you all step through that on your own, and the worksheet key is posted so you can double check your answers. But we're going to go on to worksheet problem 4. And in this problem, given the values of the enthalpy of reaction, the entropy of reaction, and temperature, determine the change in entropy of the universe and predict whether or not each reaction is spontaneous. All right. So for A, we have a change in enthalpy for the reaction, or rather the system, and that's negative 95 kilojoules. And then we have a change in entropy for the system, which is equal to negative 157 joules per Kelvin. And then the temperature is 298 Kelvin. So let's go through A together, and then we will maybe go through one more, and then I'll let you work on the last couple problems. Okay, so A. So remember, delta S of the universe is equal to delta S of the surroundings plus delta S of the reaction or the system. So those are the same thing. So I'll just write system there. Oops. All right, and then remember we said that delta S of the surroundings is equal to negative delta H of the system over temperature. Okay. So let's plug in what we know. So negative delta H of the system, so that is negative times negative 95 kilojoules. And then the temperature is 298 Kelvin. And then we're going to add negative 157 joules per Kelvin. There's a discrepancy in our units. Okay, so since we're trying to determine the entropy of the universe, we should probably stick to joules per Kelvin. So let's actually change negative 95 kilojoules to joules. All right, so we'll write negative 95 times 10 to the third joules per Kelvin, because remember, there are 1,000 joules for every kilojoule. So we're just going to multiply by 1,000 there. Okay, so when we plug this all into our calculators, so we have two negatives in the front, so that's actually positive 95 times 10 to the third over 298 plus negative 157. All right, so this should give us a value of 162 joules per Kelvin. And you can always double check my math too and let me know if I have any discrepancies here. All right, so now we need to determine if this reaction is spontaneous. So delta S of the universe is positive. So is this spontaneous? Yes, this process is spontaneous. Okay, so now we'll do the same thing for B. The only difference here is the temperature. The temperature has increased significantly to 855 Kelvin. Okay, so we said in the last problem that at 298 Kelvin, this reaction is spontaneous. So now that we're increasing the temperature, do we still expect it to be spontaneous? So delta S of the reaction is negative, which means it's endothermic. And remember from a while ago, or a few slides ago, we said that at low temperatures, an endothermic process should be spontaneous. Exothermic. Excuse me. Whew, I'm having one of those weeks, you guys. I'm sure you can relate. So it's exothermic. So we said that at low temperatures for an exothermic process, the reaction is spontaneous, but at high temperatures for an exothermic process, it's non-spontaneous. So, okay, so exothermic, let's write that down. Low temps equals spontaneous. High temps equals non-spontaneous. All right, so I'm going to guess that this process is non-spontaneous at this temperature because it is quite high. But let's do the math and see if our prediction is correct. All right, so we're going to do the same thing we did before. We said delta S of the universe is equal to negative delta H of the system over temperature plus delta S of the system. So we're just going to plug in everything that we know. So the change in enthalpy of the system is negative 95 kilojoules again. So let's convert that to joules so that everything is consistent. So we'll just multiply that by 1,000. And then we're going to divide by the temperature, which is 855 Kelvin. And then we're going to add our change in entropy for the reaction, which is negative 157 joules per Kelvin. All right. So delta S of the surroundings looks like it's actually positive because we have two negatives there. And then delta S of the system is negative. All right, but when we put this all together, we get a value of negative 45.9 joules per Kelvin. So delta S is negative, so it's less than 0. So is this a spontaneous process? No, this is non-spontaneous. So this is what we predicted, right? We said that for an exothermic process and high temperatures, we have a non-spontaneous reaction. So that is true. All right. So I'll let you work on part C and part D for this problem. And I also would like you to kind of try to predict what you think the reaction is. Is it spontaneous or is it non-spontaneous? So for instance, in C, we have our lower temperature again, 298, but this is an endothermic process, right? So if the system is absorbing heat and it's non-spontaneous because the system has a negative entropy, do we expect this to be spontaneous or non-spontaneous? So just kind of think through that, make a guess, and then do your calculation and see if you're right. All right, and then part D is right there. And we're going to stop there. Next time, we're actually going to derive something called Gibbs free energy. So this is a whole other bag of worms that we'll get into. Or I guess it's a can of worms, right? All right, so I'm going to go have some more coffee because my brain has stopped functioning clearly. And I will see you all in the next video.